So we had the indefinite integral so far. So of course there's then also a definite integral. So let's have a look at what that means. So basically the definition here of the definite integral is, well, on the left hand side you see the notation, the definite integral of some functions. Again, the same integral symbol, this little elongated s symbol, and the dx is also the same, so it's the variable that f is a function of. But now you see these additional numbers or parameters here, a and b, which are the integration boundaries. So basically we take the definite integral in a region for x between a and b. That's what this means. And what the definition is, if you see this symbol with an a and a b, these boundaries attached to it, what we want to do is, well, we figure out what is this indefinite integral function that we found before. So the big F, which upon taking the derivative gives us the little f. And what we're now doing is we're going to use that big F, plug in the upper boundary, so the b, and that will give us a number. And then we subtract from that the same big F function, but now plugging in the number a. So it gives us another number, and the difference between these two numbers, that's the definition of this definite integral. So again, this big F is of course a function which upon differentiation gives us the little f. So let me just elucidate this perhaps with an example. So let me do the example on paper. So I'm going to take the definite integral now of the function x squared plus 2 between the boundaries x equals minus 1 and x equals 2. So here we go to paper. So we are interested in the definite integral of the function x squared plus 2, which is a function of x. So the integration variable still is x, we have dx here, but now we add these boundaries. X goes from minus 1 to 2. So what's this by definition? It is going to be the function which is the indefinite integral of this, which is, well, let's write this, x cubed divided by 3, that gives us the x squared, plus 2x, that gives us the 2, and let me just add now for a moment also the c that we had all the time. I'm going to write brackets on around this. I'm going to write a big vertical line here on which I write these two boundaries, the x equals minus 1 and minus 2, and now I have to do this. So what does this mean? So I want to first input for each x that I see here this upper number here, so number 2, the upper boundary 2. So the first bit is going to be this bit with 2 inserted, so this gives us, well, 2 to the power 3, that's 8, so 8 divided by 3 is 8 thirds, plus 2 times 2 is 4, plus c, the first bit. And now I have to subtract from that, same thing, but now wherever I see an x, I plug in the minus 1, the lower boundary. So I'm going to subtract, well, what's minus 1 to the power 3? It's minus 1 times minus 1 times minus 1. It's an odd number of minuses, so it gives us a negative minus 1. So minus a third, plus 2 times x, well, plug in x equals minus 1, so it's minus 2. Again, plus c. So I plugged in x equals 2 here. I plugged in x equals minus 1 over here. And I'm taking the difference between these two expressions. So what is that? You work it out. Well, first note that we have a c over here. We have a minus here, minus c. So these two c's are cancelling, right? C minus this c. So these c's are dropping out. So in practice, since these c's will always be dropping out, we don't even bother writing them in here when we do a definite integral. So they're important when we're doing the indefinite integral. for these definite integrals, where we're looking at these two boundaries and subtracting, they will drop out anyway, so we can actually leave those c's out. They don't matter. But the other numbers do matter, of course, so let's also consider those. We have 8/3 minus 1/3, so that's 8/3 plus 1/3, that makes 9/3, or 3. We have plus 4. We have minus 2, so plus 2. And I cancelled the c's already, I dealt with those, so this is it. And now we can, of course, compute this. And this is going to be 9. So this definite integral is going to be a number. Well, what number? It's a number that we get upon taking the difference between this indefinite integral with the upper boundary, the 2 inserted, substituted for x, and the definite integral with the number minus 1 inserted. And that in total gives us the outcome 9. So let me go back to the slide then. So here we are again. So this is the computation that I just did. So I looked at the indefinite integral. I already skipped this constant c here because I knew it was going to drop out. So that's what I just explained why that's the case, because it's cancelling. It's sitting both in the upper boundary result and in the lower boundary result, and those two are cancelling anyway. It's the same c. So what we're left with is, precisely, the terms that I just computed, adding up to 9. Just a little bit of notation here. So I had this vertical bar with the a and the b. Sometimes this is denoted with these rectangular parentheses with the a and the b on the right hand side. So that's just the same, a different notation for the same expression here. F evaluated at the point B minus F big F evaluated at the point A. So why are we interested in this particular expression? Well, basically because the definite integral has an interpretation, and this interpretation is the area below a graph. So here we have some graph, function f of x, so this is the graph, this wavy line is the graph of f of x. And now the idea is that this definite integrals between x equals a and x equals b it's a number. Well, what number? It's exactly the area below this function. So you can look at the book for sketch proof. Let me also sketch this a bit on paper to provide you some intuition for why this is the case. So there we go. So we had this graph. So there's this, try to produce more or less what we had there. So here we have this function f of x, x on the horizontal axis and y on the vertical axis. So now I'm claiming that the area between this x equal a and x equal b is area a. That's the definite integral that we are sort of computing here. And the reason is, broadly speaking, let's have a look at what happens if we would take b a little bit further. So if instead we look at the number, this number here is b plus a little, we call it delta x. So the width of this slide extra bit of area, the width of that is delta x. Or what's the height? What's f of x? Of course, f is changing. So the height, this total height is changing as I move from b to b plus delta x, but not by much. So approximately the extra area that I get by shifting my b by a little bit of a little slice, if you wish, to b plus delta x. So the extra area We call this delta A perhaps. That's going to be the area of this slice, so it's the width delta x, times the height, which is approximately, to a good approximation as this width gets very small, going to be the f of x evaluated at x equals b. Write it as delta x times f of b. So what happens if I shift this upper boundary up by a little bit? This change, the rate of change, or no, the change itself of my area is proportional to how much I am shifting this up, delta x, the movement to the right, times the height. But if you think back, what's a derivative again? The derivative is how fast does something change? So here we're asking how fast does area change if I change my rightmost parameter b here to grow a little bit further. And the speed at which this is changing is precisely this little f of b. So the derivative, which measures how fast a changes of a, the derivative of a, depending on how far I choose b. So if I choose b a little bit further, it changes by an amount f of b. So we know that this function a of b is something for which the derivative is the function little f. So indeed, a itself is approximately f of b, because that's precisely what the definition was of the integral. It's the function which, if I take the derivative, gives me back the function little f. So that's a relation that defines a relation basically between this area and this definition that we had of integrals as being the object, the function, which if you take the derivative gives me back the original function. So that's basically the intuition. And again, with this in mind, have a look at the chapter I noted in the slides in the book to see whether you can figure that out. So that's just some background to have some intuition. You can also, of course, just remember, well, this definite integral, it just is the area under a graph. So here we are. So this area under this graph is precisely the definite integral of this function f of x between the boundaries a and b. So I compute the big F, I evaluate it in b, and I subtract from that the same big F evaluated at x equals a. So we have to be a little bit careful about what are these, what do we mean by area? So you might say, well, if we have this function f of x, which is a wavy line which passes through the x-axis actually. So sometimes the f is negative. Well, typically we might be interested in the shaded area here, but we have to be careful. So if f itself is negative, then we are also going to measure the area with a negative sign, the minus sign. So if you are genuinely concerned about what the area is always a positive thing, then you would have to correct for that. So if you're interested in this first bit of area, the shaded area between x equals a and x equals c1, shaded area in this sort of almost triangle. Since f is negative there, if you're really interested in the area itself, positive number, we have to add this, multiplying by this minus 1. So if in this particular case we want to know the whole shaded area, you would have to be careful to add up little bits and pieces. The first bit between a and c1, the function is negative, so I have to, if I would not add a minus, I would get a negative outcome. Well, I want to have the positive area, then I have to add or multiply by minus 1. The second bit between c1 and c2, there f is positive, so it's genuinely the area as the definite integral. Third bit again, it's little f is negative, so if I want this area, I again have to multiply by minus 1 between x equals c2 and x equals c3, and finally the final bit between x equals c3 and b, I again have to, f again is positive, little f is positive, so I can do with this the definite interval itself. So you have to, if you really want to compute areas between the x-axis and the graph without minus signs, then I have to correct for the minus signs whenever f is negative. So I have to be careful for points at which this function f, or the wavy line, the graph here, goes through the x-axis, or in other words, when the function x equals 0. A couple of properties that follow immediately, actually, also from some of the properties of the definition, first of all, and also of the rules that we had for the integral. So from the definition, you will find it's going to be pretty easy to see that if I exchange these limits, then I'm going to exchange these two terms that I take the difference of, so that f will, in terms of the big F of b minus the big F of a, will turn into the big F of a minus the big F of b, so that introduces exactly the minus sign that you see here. So if I interchange the a and the b, I get an additional minus sign in front of the expression. If I take the definite integral from a to a itself, I'm essentially computing big F of a minus big F of a, and that's of course going to be 0. If I multiply the function itself under the integral by a constant alpha, then of course the definite integral is also multiplied by the same constant, since we know the same thing holds for the indefinite integral. And again, we have some rule of kinds. If I split up the interval between a and b in two parts, the part from a to c, where c is in between a and b, and then the second part from c to b, well, then since we know this is going to be the area under the graph between a and b, well, of course, it's the sum of the area between a and, well, halfway, for instance, between a and b, plus the second part halfway between a and b to b. So again, if you just write this out in terms of the definition, you'll see that this actually is obviously true, and if not, see in your book. So this was the definition of the definite interval. So the next bit will be about what are we going to do with this. So we now know that the definite integral has the interpretation of an area. So why are we interested in areas as economists? So we're going to have a look at different applications where area on the graph actually has an economic meaning.